In this video, I will explain how to maximize utility given a Cobb-Douglas utility function and a budget constraint. So let's jump right into an example. This says, suppose a consumer has the utility function u equals x to the 0.4 times y to the 0.6. Now, a Cobb-Douglas utility function takes on this form. U is equal to a times x to the power of alpha times y to the power of beta, where x and y are your two goods, good x and good y. A is a coefficient, which in this case we can see for our Cobb-Douglas utility function, it's just a 1. Alpha, in this example, is 0.4, and beta is 0.6. So that's the general structure of a Cobb-Douglas utility function. We are asked to find the maximum utility given that the price of good x is $2, the price of good y is $3, and your total income, M, is equal to $100. Now, when we are asked to find the maximum utility, there's one really important fact that we need to know, and that is the maximum utility occurs where the marginal rate of substitution is equal to this ratio of the price of good x to the price of good y. So we know the price of good x and we know the price of good y, but we need to figure out what is the marginal rate of substitution. Now, the formula for the marginal rate of substitution is simply equal to the marginal utility of good x divided by the marginal utility of good y. And specifically, the marginal utility of good x is equal to the derivative of the utility function with respect to good x. And similarly, the marginal utility of good y is just the derivative of the utility function with respect to good y. So let's go ahead and start solving some of these values. So let's start with the marginal utility of x. So that will be equal to the derivative of the utility function with respect to x. So with respect to x, that would be 0.4 times x, and we can then reduce this power by 1. So 0.4 minus 1, that's negative 0.6. And because we're multiplying by y, we also have to include that. Then the marginal utility of y is going to be, we will have 0.6 times x to the 0.4, and then we have to reduce this power by 1 as well. So 0.6 minus 1, that's y to the negative 0.4. So the marginal rate of substitution is simply going to be the marginal utility of x divided by the marginal utility of y. So let's write that down. So here's our setup for the marginal rate of substitution. Now, when we have 0.4 divided by 0.6, that's the same as 4 divided by 6, or simplified, that would be 2 divided by 3. So really we can write 2 divided by 3. Now for x, we have a negative 0.6 in the numerator. We can make this positive by just moving it down to the denominator. So we would have x to the 0.4 times x to the 0.6, and those exponents just add up to 1. So we would have x to the first power, or just x. So let's write x. And similarly, this negative exponent for the y, we can move that to the numerator to make it positive. So we would have y to the 0.6 times positive y to the 0.4, which is just y to the first power, or 2y. So this is our marginal rate of substitution. And remember, we said maximum utility occurs where this marginal rate of substitution is equal to the price of x over the price of y. So the price of good x is 2, and the price of good y is 3. So our maximum utility will occur where these two ratios are equal to each other. So let's go ahead and set them equal to each other. We'll say 2y over 3x is equal to 2 over 3. Now to solve this, we can just cross multiply. So we get 2y times 3, that's 6y, is equal to 3x times 2, that's 6x. Notice that these 6's will cancel out, and we'll see that y is equal to x. So what this means is that the consumer will find their maximum utility when the quantity consumed of y is equal to the quantity consumed of x. So the last step to actually figure out what these quantities are is we just need to write the equation for our budget constraint. So I'm going to clear a little bit of room right here. So we found that the quantity of y will be equal to the quantity of x. The last thing we need to do is write down the equation for our budget constraint, which takes on this format. M, our income, will be equal to the price of good x times the quantity of x plus the price of good y times the quantity of y. So for our particular example, our income is 100. We'll set that equal to the price of good x is $2 times the quantity of x, plus we have the price of good y, which is $3 times the quantity of y. Now here we found that y is equal to x. So what we can do is we can plug in an x for y right here, and we'll be able to solve for x. So when we do that, we get 100 is equal to 2x plus 3 times x. So remember, we're plugging in an x for this y right here. So we get 100 is equal to 2x plus 3x, that's 5x. If we divide both sides by 5, we'll find that these 5's cancel out, and x is equal to 100 divided by 5 is 20. So the quantity for good x is 20, and we already found that the quantity for x must be equal to the quantity for y, so we can also say that the quantity for y must be 20. So this is our final answer. The consumer will maximize their utility when they consume 20 units of good x and 20 units of good y. And when they do so, they will use up all of their $100 of income, and they will maximize their utility. Now, if we want to figure out what their utility value would actually be, we can just plug in a 20 for both x and y in this equation. So we would find that u, their utility, is equal to 20 to the 0.4 power times 20 to the 0.6 power, which that comes out to, we can just add these two exponents. 0.4 plus 0.6 is 1, so we get 20 to the first power, which is just 20. So their utility has a value of 20. So that is the general process that you can use to maximize utility when you're given a Cobb-Douglas utility function and a budget constraint.